Okay, let's talk about application acceleration architecture design examples. Uh, that's the topics I'm going to talk about today. First, I will give you a architectural framework. This framework, I think, is uh, it's can be applied to the general HLS-based FPGA designs. Yeah. And the next one, I will talk about the memory access scheme. So basically, give you a few techniques that to have a efficient memory I/O access. And memory I/O access always very critical in the high performance systems. Yeah. And then in the next, I will introduce few architectural design examples. Uh, for the first one, I'd like to talk about dynamic pipeline. And currently, the HLS compiler is based on the static pipeline, and it's very conservative. But, but a lot of problem that it's not really a static pipeline. Yeah. So even though today's HLS compiler cannot handle the dynamic pipeline, that you can always do some kind of code transformations and then leverage current HLS compilers to do the work. Yeah. So I will introduce few techniques. Yeah, for the dynamic pipeline. The next one I will talk about large matrix multiplication. Yeah, and and then I will talk about convolutions. Yeah, and convolution has been introduced by the project from some of your project reports. Yeah, so most of you are quite familiar with that. And in here, I'm particularly talking about the 1D convolution, turning the 2D convolution into the 1D convolution. And why the interest is that this example give you a framework that how to handle the non-sequential type of the assets and still using the streaming and data flow models. Yeah. So that's it's a very important technique, how to turn the code which is similarly not possible running in data flow. And yeah, can make it in the data flow scheme. And the next one, I really like to introduce systolic array. And the reason why the systolic array in FPGA is so important because it fits naturally in FPGA architectures. One of the nice features is in the systolic array, they are all local connections. That's very important. We know in FPGA, 90% of FPGA resource is in interconnection. Yeah. And so in the FPGA, the interconnection is very limited. So oftentimes you will see that you could not implement into the FPGA is due to the routing. The the implementation run out of all the interconnection resources. Yeah. So that's why systolic array implementation is very much favored in FPGA architecture. Yeah. Okay. Okay. Let's go back to the for the high performance implementation. There are three optimization goals. Yeah. And the first one, we basically deal with the pipelining. Yeah, a lot of optimization effort is in how to run the pipeline with the II equal 1. So that's one dimension of a parallelism. That's test level parallelism. Another dimension of a parallelism is data parallelism. That means you do the scaling and folding on the data set. Yeah. So that's the SIMD is one example. Okay. Another critical optimization goal is how to transfer the data across the memory I/O and make the data movement efficient. And so first, that you need to have an idea. Your algorithm is if it is the compute bound, then you have to saturate the pipeline. Okay, make with data from the memory. If you know ahead that your algorithm is actually memory bound, then you should maximize the bandwidth utilization first. For example, you try to, because given the hardware configuration, there is a theoretical memory bandwidth upper bound. Okay, so as a lot of time that people could not fully utilize the memory bandwidth, as we talk about in the previous last two lecture that I talk about the DDR memory, yeah, and you know that there it's the memory utilization often is too low, yeah. So the most efficient way is increase the memory utilization first, yeah. So there are various techniques to improve the memory utilization. Yeah. So basically there are three optimization goals here. Okay. Okay. Let's talk about this framework. Okay. That's the typical when you do the application acceleration. That's the typical architectural framework. Okay. So there are key steps. Okay. First. Okay, very important. You have to separate the data movement from the computation. Like in this example, you have a I/O processing that deal with, you try to optimize all the memory I/O. Okay, and this is for the computation. Okay, why the reason you have to separate the data movement from the computation is you don't want the two things that interfere each other. Okay, once you separate them, then you can apply the optimization techniques independent from the other part. Okay, because those two can have different optimization strategies. Yeah. So that's the first step. Okay, look at your problem and separate the data movement from the computation. Okay, and the next step. Okay, and for these two parts, which part you should work on first? The data movement part or the computation part? I would suggest you work on the data movement first. Okay, because these two actually affect each other. Yeah, and if you don't do things right, that you may do many iterations and get the result. Hardly get any hardly to get the result. Move on. Yeah. So you optimize. How do you do the optimization data movement first? Then you can have the PE. You can have write a pseudocode, a very simple code. Okay, to simply to make the computation with II equal 1. Okay, and those code is not real. Okay, simply to make sure the data is moved the way you want. Okay, so make the computation not a bottleneck. Okay, and then you focus on moving the data and doing the right scheduling and apply all kinds of techniques to improve the memory bandwidth. Okay, and then for optimizing the memory bandwidth, the techniques you apply is you try to analyze the memory access pattern. So you can apply the polyhedral analysis, okay, to extract the memory access pattern. And then you can do the access transformation. I will talk about the techniques in today's lectures. Yeah, there are various techniques to do the code transformation to improve the memory access efficiency. Okay, so you do the memory access extraction, and then you do the code transformation to do the optimization. Okay, the step. And then after you done this part, then you work on the the processing stage. Okay, for the processing stage, the steps, okay, is first do the data parallelism first. Okay, make sure all the data parallelism that can fully utilize the data bandwidth you can provide. Okay, so that's like a SIMD. Yeah, so you have a multiple computing units. Okay, you set up the folding, yeah, and to maximize the data bandwidth. And then you work on the PE, work on the pipeline. Okay, make sure the data rate or the II equal 1. Okay, and then to make and you have a multiple stage of a PE. Yeah, so you work on the PE on each stage, and the next step is you try to streaming data between the PE. Okay, so then you design the data flow scheme. Yeah, and last at the last you try to make like a historical array. That means you try to uh, formulate your problem so that all the data is localized. Okay, yeah, and the historical array is the most efficient architecture for doing all these computations. And yeah, to apply the historical array on your problem, you do need the insight on your computation and on the data paths and the data flows. Yeah. So that in the lecture, last topic in today's lecture, I will talk about the historical. Yeah. And then during this process, that the goal really is streaming data. Okay, remember the FPGA. The most important reason that FPGA outperforms CPU and GPU is the data flow. Okay, so you can customize your data path and apply the data flow. Okay, so why is it so effective? Imagine that the CPU could run maybe 3 gigahertz, and FPGA maybe max you run at 300 megahertz. So in terms of clock speed-wise, CPU is 10 times faster than FPGA. Yeah. So why FPGA can still has a one or two order performance over CPU, and why FPGA actually running with lower power. That's all because of data flow. Yeah. So when you're doing the design, you really need to think about using the data flow, using the streaming. Yeah. So in today's lecture, all the example I will use streaming. Yeah. Make sure you all familiar with how to turn your algorithm into a data streaming design. Okay. And next, you have to consider design for scalability. That's very, very important. You have to consider scalability from the very beginning. Yeah. Imagine that, let's talk about different level of scalability. For FPGA, okay, for you can consider for FPGA chip, they have multiple SLR. SLR is a die, okay, and they can interconnect multiple die together become a FPGA chip. Okay, and FPGA, you can have a multiple in a system. You can have a multiple FPGA. Okay, connect to one host, and multiple FPGA can interconnect with other FPGA through the network. Okay, so for different levels, they introduce different delay. Okay, and the interconnection resource getting less and less when you scale up. Okay, so how do you partition your problem that can be scaled up that using larger capacity of PGA or more SLR, okay, or even multiple FPGA chip, or even computing resource across network. Okay, how do you partition your problem in a hierarchical way that have a different for each level have different communication overhead? Yeah. So that's a very interesting problem, and especially for high performance computing, that people apply all kind of techniques to do the scalability. Yeah. So that's another interesting topic that you might consider, yeah, in your research or in your future study. Yeah. Okay. So here I give you a basic the architectural framework for application acceleration. Yeah. And I would like to discuss more detail for each of them. Okay, let's start with the memory access transformation. Okay, so in here, mainly we want to optimize the efficiency of all chip memory access. Yeah, if you recall that the OI, yeah, we talk about the operation intensity. Okay, the OI. So basically, it's defined as giga up over byte. Okay, and the byte here, we are talking about external memory. Okay, so we want to increase the operation intensity by using less external memory access. Yeah, for doing the operation, you definitely need to access the data. You cannot reduce the amount of data accessed by the computation. However, we want to reduce the amount of memory access off chip memory. That's our purpose. So we like to cache things into on chip memory. Okay, you access on chip memory, then you won't lower your OI. Okay, but however, there is only limited amount of memory in the FPGA chip. So how do you efficiently use those buffers? That's the topics we like to explore. Okay, let's take a very simple example here. Okay, that's memory access extraction. Okay, that's a very simple example that you basically reading data from the memory array. Actually, you access the data from two different regions of the A array. Okay, and you add them together and write to a B array. Okay, so if you write the code as simple as this, then let's see what problem you will encounter. First, okay, you access the interface multiple times in the same pipeline. In one iteration, you access A array to A array, okay, and write to B array, okay. And also, this kind of coding allows only the single memory access, could not do the burst access. And what's worse is this part. Okay, you can see that you access the A array, however, from two different regions. So that's the A array. Okay, you access the lower part and lower half and upper half, and these two parts of the data may falling into in the DRAM in different page. Okay, so you see every time you access, you create off-page access. Yeah, if you remember the DDR memory access behavior, you know the off-page is you pay a lot of penalty for off-page access. Okay, and what's worse is you can see you read the A array and then write to the B array. So there is a lot of mix of read-write access. Okay, so this kind of code is really bad for the DRAM, external memory access. So for this code, you may probably less than 10% of DRAM utilization. Okay, so we would like to change the coding. Yeah. So first, apply the first principle that we want to separate the memory I/O access from the computation. Okay, so the original code that you have a computation directly interface with the memory I/O. Okay, so right now we want to separate the memory access from the computation. Okay, so let's look at the read A this part. Okay, that's how it's coding. So first step is if you look at this code that you want to do the burst access to the memory and then convert to streaming access. So that's the way you decouple the memory I/O from the computation. For the computation, you really like to have a streaming data access, okay? Because that's the most lower resource because there is no memory buffer in between, okay? And also that's much less latency because that's data driven. Once the data comes in, the computation starts. Okay, so it's lower latency in doing this way. Okay, so let's look at the how you read the data. Okay. So in here, it creates a buffer. You use a buffer to cache half of the data. Okay, that's the case that this amount of data can be fit into the FPGA memory. Okay, and then you use a for loop with a pipeline. So with this kind of coding, you know that you can do the burst access on memory. Okay, you all know about it. Yeah. Okay, and then for the second part, okay, for the second part, you when you read the data into the internal buffer, and then you try to stream out the A0. Okay, that's the A0. You're streaming out, and at the same time, you try to read another part of the memory. Okay, so actually, these two parts can be running concurrently. Yeah. So you're reading this and reading, you first fill the buffers, okay? And then while you reading this and streaming out these two, actually it's a concurrent. And this kind of coding, that's the backend, the streaming part. Okay, so this part you can still do the burst access on the second part of the A array. Okay. And for PE part, that's a streaming interface. Okay, so you can run when the data comes in, then you can do the operation. Yeah. So in here, this example demonstrate two things. One is you separate the memory access from the computation, and secondly, you apply for this part, you can apply all the memory access optimization scheme. For example, in here, you can do the burst access, okay? And then you can even enlarge the data width, okay? Although this code doesn't show that, but you can always do that to increase the data width. And the streaming rate really depends on how fast your processing engine is implemented. Okay, yeah. So this solution provide separate the compute and memory access. Okay, allow for burst access, and then you can prefetch the A0, the one lower part of the memory array. Okay, and the PE processing agent can access the two memory string in parallel. Okay. Yeah, so this give you an idea how to do the memory access traction and apply memory access fast memory access. Okay. So in the previous example, actually using some kind of memory buffering. So memory buffering is very important. One of the advantage using the memory buffering is because the DRAM has an inconsistent data rate. Okay, and because the DRAM is accessed by multiple threads of other processing. Yeah. So there's no guarantee or no constant data rate that for this processing engine. So you do need a buffers. Okay, and these buffers you can reel ahead in a more aggressive pace. So that means in here you can apply many techniques which is decoupled from the processing engine. Okay, so for the string here, you can have a wider or narrow, okay, or even slower or faster. Okay, so you can really decouple these two. You don't need to sync each other because once you sync each other, then create a lot of overhead. Okay, and by doing this way, it's easier to do the design. Yeah, so that's why buffer is a very useful resource. So on the memory side, you can apply using wider data bus and doing the bursting, and you can even have a different clock rate. Yeah, and you know this part is on the FPGA, and this part is the memory controller. Okay, and the memory bus running very fast. The memory controller normally there's a hardwire. Okay, so it's run faster than the FPGA part. So actually, in this part, you can have a different clock speed. Yeah, so you can run at a different clock rate. Yeah, and here you can leverage multiple channel of DRAM. So the PE side really don't need to worry where the data located. Yeah, and this guy does all the address translation because it can do the address interleaving to provide higher bandwidth. For example, the DRAM can have a multiple channel of DRAM, and you use the address interleaving scheme, so that you can increase the data throughput. Yeah, aggregate all the memory channel throughput together. Yeah, and when you streaming to the PE side, you actually streaming to PE at the compute rate. Yeah. So actually streaming when the pop of the data is on the PE rate. Yeah. Okay. Yeah. So right now, so for the memory buffering, the question comes to what factors affect the buffer width, buffer size. Yeah, that's a very critical question. How much buffer you need to allocate? What factors affect it? So you can understand the throughput is one reason. The throughput, and the consuming rate. Yeah. Data width and then clock frequency. There are all kind of there are many factors affect the buffer size, then you need to do the detailed calculations. Yeah. Oftentimes you really don't need to prefetch too much data. Yeah, as long as the buffer size, the one simple principle is the buffer size. If the memory bandwidth much higher than the PE computation data throughput, then the buffer size just large enough to bridge the latency of the DRAM access. Yeah, and more buffer doesn't help. Yeah, as long as you can sustain the streaming rate, that will be good enough. Yeah. So memory buffer design, yeah, is important. Yeah. Okay, another topic is about memory striping. Memory striping, basically you have a multiple channel of DRAM. Okay, and then you can aggregate the data from the data rate from the memory channel. Yeah, and you try to interleave across the multiple channel memory. Yeah, and the issue is how do you do the interleave? Interleave, basically you have an address, okay, and then you choose a portion of your address space. For example, suppose that's a 4K page, okay. Then you use for example, use the A12, A13. If you have 4 channels, you use the 2 address line to interleave across these 4, so that you can have a on-page access from the 4 channel at the same time. Okay, that's one thing. But with this interleaving, that another thing is you really want to increase the throughput. Okay, let's say the streaming needs 4 times of the memory channel throughput. Okay, in this case, you will use the lower address as the interleave. Okay, if a streaming, let's just take an example. Streaming size is 64-bit. Okay, and then that's 8 bytes. Okay, and then it's because that's 4 times channel width. So you actually each time you try to transfer some 32 bytes. Okay, however, each cycle, each channel can only provide, because there's a 64-bit memory bus. Okay, that's 8 bytes. Yeah. So how do you do the interleaving? Yeah. So then you will use the address A4, A5 to interleave these 4 channels. Okay, so that you can aggregate the memory channel bandwidth to satisfy the streaming channel the streaming throughput. Okay, so for this you try to implement a scheme that you actually internally you try to you can decouple these two, you know. For this PE still doing the sequential access, but inside you try to recreate the memory access address. In here you will have a memory access memory address generator. Okay, and then you try to use the A4, A5 to direct to different memory channels. Yeah. Okay. So let's talk about what factor affect the striping scheme. Yeah, that's just one example. Yeah. Okay. If you have any questions, yeah, you can raise your hand. Okay, another technique is if you can analyze your computing data assets that you can use in the cache. Yeah. For example, this code you are all very familiar with that. You can have a this is you have the spatial locality. Yeah. Okay. So with this locality, then you can use the cache techniques, and you find out that you actually repeatedly use the previous uh, access data, and each time you have only one new data need to access. Yeah. So you provide the template 012 as a cache data. Yeah. To save the reduce the memory access. Yeah. So that's the memory cache scheme. Yeah. Okay. So there are other techniques to optimize the memory access, and I just illustrate three examples, give you an idea. Yeah, the techniques you can use. Okay. Okay. Next, let's talk about dynamic pipeline. Yeah. As we talk about the HAS compiler, it has the only support the static pipeline scheduling. That so yeah, so it's only perform the static pipeline, and since the HAS compiler it doesn't have the global view on the whole algorithms, so it tend to be very conservative for handling the loop carrier dependency. Yeah. So that so oftentimes that the HAS compiler could not to synthesize the RTL code run at the II equal 1. Okay. And in academically, there are a lot of research going on to incorporate the dynamic pipelining techniques. Yeah. And try to capture the human architectural level thinking techniques into the HAS compilers. Yeah. And however, people doing this uh, research, and they try to transform the C code and then use existing HAS compilers. Okay. The benefit is for school doing the research, they are not have the resource to implement an HLS compiler, because it's a huge effort to do the to design HLS compiler. So that's the approach they are doing. And before that techniques mature and adopted into the HLS compiler, this maybe take 2-3 years to have this feature incorporated into the HLS compiler. So by that time, that we can learn from those research papers and try to do the code transformation by ourselves. Okay, yeah. So the following example is basically I adopted from two research papers. Yeah, and actually there are many other papers talking about various techniques. So I will encourage you that based on the problem you want to solve, you may search for those research papers, then apply that techniques. Yeah. Okay. So the dynamic pipeline, I will introduce three dynamic pipeline techniques. One is from the RISC-V. Yeah, then that was introduced, I think, a few weeks ago. That's the dynamic scheduling. Yeah. Another technique is speculative loop pipelining. Yeah. And another is the loops with uncertain dependency. Okay. If the loop loop carrier dependency is uncertain, then HAS compiler tend to be conservative. Yeah. And then so we have a coding techniques to avoid to improve the II. Okay. Okay. Here I just simply brief on the RISC-V HAS implementation. That was introduced before. Okay, it uses dynamic scheduling. So that means the pipeline we still synthesis with II equal 1. Okay, the code HAS compiler can synthesize the code with II equal 1. However, there are certain pipeline dependency happen. So there's a data hazard. For example, there's a load to use case. Okay, you load the data and then you do the operation on it. Okay, so at the memory stage, that the data has to feed into the next stage, and you don't have enough time to do that. Okay, so you have to store the pipeline. You have to store the pipeline. Okay, this pipeline storing. So basically, this instruction and this instruction, this part is II equal to. Okay, if without this data hazard, you run at IA equal 1. Okay, so the way it does the store. Okay, so from the coding, you need to know how to write the code to perform the store behavior. Okay, in here, I will say that the first you will need to do the detection. Okay, the detection is at instruction decode stage. Okay, instruction decode, and then you find out that the previous instruction is low. Okay, and the current instruction is a low to use case happen. Okay, so you will do two things. So you have to emulate this pipeline behavior. If a pipeline is stored, okay, actually this instruction is already fetch. Okay, this subtract operation actually is already fetch and going to the decode stage. Okay, and then so what you need to do is you make the following pipeline stage is a no up. Okay, and then you want to refetch the instruction. Okay, so that's the feedback loop. Okay, there are actually two loops here. One is you tell the following pipeline stage is no up. Okay, and also you feedback the signal to the fetch stage. In the fetch stage, you freeze. Basically, normally at the fetch stage, you will advance the program counters. But if a store happens, then the program counter will not increment. Yeah. So that's the way you implement the store. Okay. Yeah. In here, what we would like to say is for dynamic, for doing the store, how do you write the code to perform the store behavior? Okay. Okay, let's look at the next example. That's called speculative iteration. Okay. And for example, this code. Okay. So the pipeline, the II, cannot be less than the latency to calculate the assay condition. This is the assay condition. Yeah, there are two multiplication here. So this things cannot finish in one cycle. It cannot do in one cycle. So that's why the II cannot be one. It has to be greater than one. Okay, in this case, this operation takes 3 cycles. In this example, it takes 3 cycles. Okay, to detect the acid conditions. So when you do the pipeline, then take II equals 3. Okay, it takes 3 cycles to detect the acid condition and decide whether next iteration can proceed. Okay, so we really like to this pipeline to run II equal 1. Okay, and this technique is called a speculative pipeline, and that feature is implemented in Intel HLS compiler, but not in the Xilinx HLS. Okay, so how do we do that? Okay, let's take a next example here. Yeah. Okay, that's the code. Let's look at this code. Okay. So in here, there's a S function. S function is a three-stage pipeline. S function is three-stage pipeline. 1, 2, 3. F function is a one-stage pipeline. Okay. So for this, so the iteration latency. Okay. What is the latency for iteration? Is 3t because this function takes 3t. Okay. So what is the II will be in this code? So what is this II? Okay. So actually the II equal 1. Yeah, because based on if you remember how do you calculate II? Okay, that's the equation you calculate the II. You have the loop latency 3. Okay. And the dependency distance. Actually, in here, you can see. So when you calculate the S, and 3 iteration later, okay, you can see the data. Actually, the 3 iteration later, the data will be used. Okay, so distance actually is 3. Okay, so for this case, the II equal 1. Yeah, so don't be fooled by this equation. Yeah, you think that S is 3, then the II cannot be done in 1. But since the data only be used 3 iteration later, so there's no problem. You can still run II equal 1. Okay. Okay, so this example is much more complicated. Okay, let's look at this code. Yeah. Okay, this is a loop. Okay, the loop decision exit condition is on X. Okay, but the X, how do you determine the X? Depend on the previous X, and there is a C function. The C function actually is the latency equal to. It will decide which value X will be. Okay, if the C function is true, then the X value takes 3 cycles to get X value. Okay, if the control function, the C function is false, then that's a fast pass. F function latency actually is 1 here. F is 1 here. Okay, so for this problem, so how do you design this pipeline? Okay, so the most simple-minded, if you give the job to HLS compiler, you will get II equals 3, like this example. Okay, so after 3 cycle, then you decide the although yeah, at 3 cycle, then you you start next iterations. So that's a very simple minded. Okay, so or you can apply the previous dynamic pipeline techniques. Okay, so this one is a static that the current HAS compiler will perform exactly like this. Okay, give you I equals 3. Okay, now let's apply the dynamic pipelining. Okay, like the RISC-V example. Okay, so you will have a II equal 2 because once you know the control function, yeah, if the control function is true, then you store 1 cycle. Otherwise, if it's false, then you can immediately proceed. Okay, so the average II you get like 2 point something. Okay, better than 3. Okay, so that's you apply the dynamic pipelining. Yeah. How about let's take a speculative pipelining. Okay, speculative pipelining, that means we speculate this function is false. Take the fastest path. Okay, until you find out it is not. Okay, if it's not, then you have to do the recovery. Yeah, that's many of the processor. Today's processor is a speculative processor. Yeah, so they apply uh, intensively the speculative techniques. Yeah. So let's take that's the example here. Okay, that's a speculative pipelining. Okay, in here, so you simply run the II equal 1. Okay, until in the third iteration, the C function find out this C function. We find out that it's the X evaluate is true. Okay, because it is speculative to be false to take the fast path. Once the evaluate is true, then it will store the pipeline. Okay, until they get the result from the slow function. Okay, and then that's the true X value you can get. Then you restart this pipeline. Okay, so so let's say assume you have a 20% will miss speculative rate. Oh, then what's the average II? So there will be 80% at II equal 1 and plus 20% at II equals 3. Okay, so that's how you get the II average like 1.4. Okay, so that basically that's a speculative pipelining. Yeah, and so let's see how do we code write the C code for this speculative pipelining. Yeah, and there's another key concept. Let's go back to the previous page. Okay, in here, okay, so you can do the speculative, yeah. But however, there's one important thing is you want to make sure there is no side effect. No side effect. Okay. So what's the side effect? It's things that you cannot recover. Okay, because you speculate something and then you produce the result. Okay, and if you speculated wrong, then you need to be able to recover the mistake. Okay, So if you speculate something and generate a result, and that result cannot be recovered, then you cannot apply the speculative. For example, one example, what things is not being able recover is you write to external memory. You write to external memory, and for that, it's very hard because the external memory, when you update an external memory in computer science, we call it becomes globally visible. Okay, so let's say you have a processing unit, PE, and you have a local memory. You have a cache, your local buffer. You have another PE, okay, and you have a local memory, and those both access the global memory. Okay, once you write the data to the global memory, that's the external memory. Then people can get the data. Other process of data can get the data. Once they get the data, then it's very difficult to recover, to have other guy to restore the context. This thing is very, very complicated and almost impossible to do that. Okay, so when you do the speculative, then you don't want to write to the external memory until it's proven correct. So the techniques you do is, if you want to update the result need to be updated in the external memory, instead of writing to external memory, you write to an internal buffer. You write to the internal buffer until it's proven the speculation is correct. Then you flash to the global memory. That's a very important technique. And in this example, I will explain that because it's applying this technique. I hope you get the idea. Yeah. Okay, let's say go back to this example. Then how do we write the code to transform this code? Okay, so that's how we're gonna do it. Yeah, hopefully I try to explain this code. Hopefully you can understand. Yeah. Okay, that's the original code. Okay, and the only difference from the previous code is it has an actual H function. Yeah, but it really doesn't matter. Yeah, so what we really care is this part. Okay. Okay, so as I said that in order to recover that, then you have to save. You have to save the context. Okay, although the pipeline keep going on, okay, and then normally you don't save the context for the previous iterations. Okay, so that's why I mean when you recover, then you have to recover the context before. Okay, so all the context you have to save. Okay, yeah. So the one important thing is that you have to save the context. So that's for recovery. Okay, in here, what context in this code? Okay, you have the C function, you have the C function. Okay, you have a S function, you have the F function. Okay, and H. H actually we really don't care. Okay, so you have to save them and save in a FIFO. Okay, save in a queue or FIFO. In this example, let's look at this example. The C function has a 2-cycle latency. S function has a 5-cycle latency. Okay, F function is 1 cycle fast. Well, so that's why we want to speculate. Okay, speculate on the fast path. Okay, the fastest pass is 1 cycle, so you can achieve II equal 1. Okay, for the speculation. Yeah, and then you save all the previous result. Okay, so so this here that's an array. Okay, that's basically that's the FIFO. That's the FIFO for the C function. For the that's the miss speculate. That's S function. Okay, and that's the F function. So that's so basically you save the X. You save the X from the fast path because that's why you default speculated. Yeah, you save it in the queue and look at here. In here that you the current control function. Yeah, it's you got the data from the 2 cycle before. Okay, because the C function is a 2 cycle latency. And in here, S function is a 5 cycle latency. So you get the data is a 5 cycle before. Okay. So you push the function result into the FIFO. Okay, and then you jump into the that's the state machine. You do need a state machine. The state machine function this way. Okay. Initially it's in idle. Okay. And then you come to the field. Field basically is the C function. Okay. The C function take 2 cycles. Okay. The latency is 2 cycles. Since the transition already take 1 cycle, so you stay in field state for 1 cycle. So the count means latency counter. That's the counter. It's counter latency. Okay. Then so you wait 1 cycle. Wait 1 cycle, then you can get the true C function result. You get this C function result. Okay. If the and then you go to a wrong state. So if the control function is false, that means that you speculative right. Okay. Okay, because take the fast path. In this case, you can commit this result, and then you continue in the wrong state. Continue in the wrong state, and then if you find out the control is true, that means the speculation is wrong. Okay, then you have to go to the take the F function result, and F function is a 5 cycle latency. And C function is a 2 cycle latency. So there's you have to wait 3 more cycles to get the S function result. So you have to store. Store basically you wait the C function pipeline, the S function latency pipeline. Okay, and then you count 2. They basically the 3 cycle latency difference because the age occupy 1 cycle. So you wait 2 cycle in the store. And then you come here, then you do the rollback. Okay, when you do the rollback, that you select the value, select in here, you select the value from the S function. Yeah, and then you write to the X, and then you get a rollback. If it's rollback, then you have to change. You have to change the X value to the remember the miss is from the S function. That's from the S function. Yeah, rollback that you basically change the context restore to with the S function data. Okay, so that's the when you run the pipeline that this display this code. Yeah. Yeah. So for this example, it shows how you write the code. Remember, this coding is very much different from the algorithm style HLS. Remember, this kind of coding is very much like structural design. Yeah. Okay. So people will think that HLS design is hard to be compatible with human manual RTL design. To tell the truth, it's not true. Okay. For this kind of design, the average designer, I don't think the average designer has the capability to do this kind of design. Even they manual do the the RTL code. Yeah. So based on my experience, you got to be a very skillful senior logic designer in order to design with this level of complexity. Yeah, most of average logic designer could not do that. Yeah, and what I really like to teach is to write the C code with the HLS compiler, and you get the result compatible or better than the RTL design. Yeah, so that's why I in this course I introduced structural design. Yeah, most of the people don't teach structural design. Yeah, so to do that, you really need to know how to do the structural design. Yeah, with this kind of a code transformation, then I believe you can design a very competitive, high performance design. Yeah. Okay. Any question? I'm not sure whether you follow me. Yeah, I probably should get feedback from you. Can anyone acknowledge that you got what I talk about? Can anyone respond that you understand or you don't understand? Can you write in the message? Say simply tell me you understand or not understand, or you say yes or no. Anybody? Yeah. Mostly. Okay. Good. Okay. Mostly is good. Good enough. Yeah. Just yeah. You maybe you come back to study this code in greater detail. Yeah. Yeah. Okay. You understand the concept. Okay. Good. Great. Yeah. Yeah. Concept is important. Yeah. Then when you do the implementation, yeah, remember, yeah, what you what you what you know. Okay. So let's move on. Okay. Okay. The next one is uncertain and non-uniform memory access. Okay. Um. So let's take this example. Okay. This is a uncertain dependency because the M is a variable. It's a unknown. It's not known at the compile time. Okay. It's a very open. Very often you will see this kind of code. Yeah, this kind of code happen in matrix decomposition or triangular matrix computation. Yeah. So for this kind of code, the HLS compiler will take conservative approach, assuming m equal 1. Okay, so that means the II definitely cannot do cannot be 1. Yeah, because the value will be used by next iteration. Yeah. And so in here, we like to restructure the code so that even m is available, the HLS compiler still can perform II equal 1 until that the real dependency happen. Then you stop the pipeline. Okay. So the technique is break break the pipeline execution at iteration I equal m. Okay, so that means when the iteration I reach m, that means it has to use the value from the previous iteration. At that time, then you stall the pipeline. Yeah. And before that, you run the pipeline at II equal 1. Yeah, until the data dependency really happens, then you stall. Okay. So basically that's the techniques. Let's look at this example here. In here, this loop, okay, so it's two cycle. Yeah, if m equals 0, then there's no dependency. There's no problem. So the array index can every cycle you can advance one array index. Every cycle you advance one index. Okay. And if m equal 1, let's say what happened? Okay, m equal 1, this thing take a 2 cycle. And if you want to do the II equal 1, then that means the next cycle you advance the index. Okay. However, the data produced at the cycle 3 here, and the next iteration need the value. So this conflict. There is a data contention. Yeah, data hazard happen. Okay. And if m equals 3, then there is no problem. So you can see that these things produce at 2 cycle. Yeah, the latency is 2 cycle later. Yeah, and the next iteration, the II can increment. Okay, until the iteration I equals 3. Okay, it's already in the fourth cycle, and the result produced at the third cycle. So there's no problem. It's safe. That's the right value. That's the read where the read happens. So this is safe. Okay. So you can see that depending on depending on the m, you can have a different pipeline II. Okay. Let's look at here. So I will introduce the code here later. Yeah, let's introduce the concept here. The L is the period of the dependent read access will violate the iteration memory dependence. Basically, the L is the loop iteration, the latency, the iteration latency. That's where you generate the right value and you will use the value. Okay, it takes the time generate the right value. Okay. And in this example, the L equals 3. Okay, in this L equals 3. Okay, then you know that if I equal 1 is not safe. I equal 2 is not safe too. Yeah. So it's safe when I equals 3. Yeah. Okay. So the D is the dependency iteration distance. Okay, which is the M. Which is the M. Okay. So if you recall how you calculate the II, so you have the iteration latency or the latency to generate the variable C, and the iteration distance that the C will be used. Okay, so the II is the maximum of the latency over the distance. Okay, so in this example, yeah, and the L equals 3, and we want the code, okay, the M, basically we reverse that. Yeah, let's say that we like to II equal 1. Okay, so what is the safest distance? That's the M. Okay, that's the M we want to find out. Okay, so there will be L equal divide by II minus 1. So in this case, M will have a conflict. Yeah. Okay, there's a dependency iteration distance. That means that there will be a hazard happen if M between 1 and 2. Okay, so during this period that you will have it's not safe. Okay, yeah. Okay, so in here, so that's so right now the M, if it's 1 and 2, then it's not safe. Yeah, and so if M equals 3, they will be okay. Yeah, and depending on the M. Okay, then so let's look at the code how it's handled. So during the conflict region that you can in here that is safe because the real value is not being used. Okay, yeah. So let's say so we already calculate M is between 1 and 2. Okay, so for the iterations that if the M is in the 1 and 2. If M is greater than 3 or 0, if M equals 0 or M equal or greater than 3, then there's no problem. Yeah, right now L equals 3, right? So in this case, that you can do the always fast pass. Yeah, so II equal 1. Okay, so if M greater than 1 or 2, then you need special handling. Yeah, and that what you will do is that's you split the loop. Okay, based on M. Okay, so basically this loop is put into different sections. So the distance is M. Okay, within one section. Okay, then if within this section that you can have a pipeline II equal 1. So whenever you reach the iteration reach the M, okay, the iteration reach M, then you have to wait for the result finish, then you can proceed. Look at here, the code how you write is for this for loop, okay, for this loop you will have a II equal 1. Okay, and for this pipeline loop, then you don't have a pipeline. The inner loop can force a II equal 1, and the outer loop then you cannot pipeline. Okay, the outer loop, this outer loop doesn't have a pipeline. Okay, that means whenever you reach the M, the index I, when you reach the M, I equal M or I equal 2M or I equal 3M, then you have to wait for this pipeline flush. You have to wait for this flush. Okay, because the dependency happened. Yeah, and within this range, I plus 1 to I plus 2M, within this index range, you can have II equal 1 because the data will not be used. Okay. So that's the code that look at this code is important. Yeah, you only do the pipeline I equal 1 in the inner loop, and the outside loop it doesn't have it cannot be pipeline. So it cannot be pipeline. That means you have to wait for this loop flush. Flush means the pipeline to the end of a last stage and get the result. Then you can start next iteration. That's how you implement the code that you can have II this session you can have II equal 1. Okay, when reach at the m I plus m, then you have to wait for previous pipeline flush. Okay, when it's flush, then you start doing the another pipeline. Yeah. Okay, so that's the techniques. People try to put this into the compiler to restructure code in this way. Yeah, but yeah, it takes a long time to put it into the HAS compiler. So why not we just learn the techniques and do the code transformation by ourselves. And there are quite a lot of people talking about different pipeline scenarios and propose the code, different code. So yeah, you can do some research and find out papers talking about this. Okay, at this point, I would like to take a short break. Otherwise, it would be too much material for you to consult. Let's say, let's come back to 10:50. Yeah, 10:50. Let's take a 5 minutes break. Okay. Okay. Here, let's talk about the matrix multiplication. Yeah, in here, specifically, I'm talking about large size matrix. Yes, very large matrix that cannot fit into the on chip memory. Okay, let's simply take an example that let's particular. Let's say we have a AK by AK the matrix. Okay, so you have a 64 mega entry. Okay, and each entry is 4 bytes, let's say integer. Okay, and then you have A must be equal C matrix. So you need 3 matrix. Okay, so then you need over 700 megabyte memory. So it simply could not fit into the memory. Yeah. And let's say that also, if you want to achieve 32 giga ops operations, okay, yeah, you want to do a accelerator that provides you 32 giga ops operation, and for each operation, take the 3 operand, okay, and then you can see that so that's a 12 bytes of data. Okay, so for that, you need to have a data throughput. It's around 384 gigabytes, the data throughput. If all the data has to get from system memory, from the DDR memory, yeah. And we know for one channel of DDR memory, yeah. Let's say you run at this 24 giga DDR, okay. And each DDR is 8 by 64-bit bandwidth. So each channel only provides you like 12 gigabytes. Yeah, it's way under the data bandwidth needed. Yeah. In here, I simply illustrate an example that when you deal with a large size data size, that the 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 data movement, the bandwidth requirement, and the amount of data need to store that it's beyond your the you must apply very specialized skill to handle this kind of problem. Yeah, so that's why if you guys remember when we interview for talk about the final project, Yeah, and if your problem size is small, you don't really solve a problem. Yeah, you have to face the big data size in order to have a solution useful. Yeah. So here I'm talking about how people solve that problem. Okay, that's the problem statement. Okay, especially for the large matrix multiplication, and that's a very typical code. Yeah, you have a matrix which is n by k and b matrix k by m. Okay, and then you can we use a cube to represent these matrix multiplications. Yeah, so if you have a array which is n by k, you have a b array, yeah, which is k by m. So the result C matrix is n by n. Okay, okay. So so there are a few problems. One is let's look at the one issue is the loop carry dependency. In here, particular, let's say that you are solving a scientific computation, okay? Uh, then people use a 64-bit double precision operations. Then the latency will be greater than 1. Yeah. So for this operation, okay, that greater than 1 cycle. So the inner loop, okay, you simply cannot get the IR equal 1. Yeah, because the data, yeah, in the loop, the data has to calculate and use for next iteration. Yeah. So for this kind of problem, loop carry dependency, then you will apply loop transformation and interleaving. That's the techniques that we're gonna to explore. Another issue is you for large memory array, you deal with the large memory I/O, and you don't have enough on-chip buffer. Yeah. So in this case, you have a very poor operation intensity, very poor OI. Yeah. And also, even worse, on the on-chip memory, it's not even able to fit one row or column the on-chip buffer. Okay, for example, if you have a 8K by 8K array, so one row the data is 8K by 4 bit, so you need at least 24K. Yeah, and then you need to feed another one column of buffer. So even you cannot fit the one row or column into the on-chip buffers. So in this case, then you have to apply not just cache, you need to have a very smart I/O scheduling. Yeah. So that's the techniques. Yeah. Another problem is considering the FPGA limitation. As I said, FPGA has a very limited routing resource, very li limited interconnection. Okay. So if for this matrix multiplication, then if you want to provide n degree of parallelism, so they will have like a 1 to n or n to 1 connection. That's needs a lot of fan out and fan in. And that has to connect globally. Okay, for example, one entry that you have to, if you want to do the parallel operation, for this one entry, A element, one element from A, then you have to feed into K element to for the B array. Yeah. Then you create a routing problem. Yeah. So if you cannot finish the implementation, then you don't have the accelerator. Yeah. So in this case, people solve with data flow systolic array. Yeah. So we will introduce the techniques, yeah, for these issues. Okay, let's say first is a loop carrier. This loop carrier dependency. Okay, so the so then we let's say that we want to do instead of we use one row of the A array, one element A array, and then multiply k element from you use one row A and times k element from B matrix. Yeah. Instead of we do that, we try to do the interleaving. Yeah. So in this case, we prepare n accumulation buffers. Okay. Yeah. Then this accumulation buffer. Okay. Then for the inner loop, for this loop n, it only be used in the next k iteration. Yeah. So you will after m iteration, then you use the acceleration buffer again. Yeah. So as long as the this operation latency is less than the m cycles, then you can have this iteration I equal 1. Okay, so that's why it says here loop carrier dependency can be solved because each location is only updated every m cycle. Every m cycle you update the accumulation array. Yeah, and another nice thing is for the ABC matrix, all read in a continuous fashion. For example, in here, for the A array, okay, then you can do the burst on K because increment by K. Yeah, and you look at the B matrix. Look at B matrix. It, you continuously read from the look at the index is M. Yeah. So normally the matrix is stored like this way. Yeah. For each row. Yeah, and then you have continuous content for the column. Yeah, that's column 0, column 1, column 2. That's a row major storage type. Okay, that's how you arrange the data in the system memory. So if you read column wise, then you can do the burst. Okay, because it's in consecutive locations. Yeah. So when you do the loop transformation, you actually exchange the loop k and m. Okay. Normally the k is the inner loop. Yeah. Right now you change m as the inner loop. Okay. So that's the loop transformation techniques. Yeah. Okay. So and also each A array, each A matrix is only read once. You just read once for the m iterations. Yeah. Okay. So that's the issue I talk about. This A element has the fan out of m. Okay. You have to fit into if you try to enroll this one, okay, so that means you have a m multiplication, and this a value has to fit into m multiplication. So you have a m fan out. Okay, so this one is as I say, it's not good for the FPGA. Yeah, and that problem will be solved later. Yeah. Okay. Okay, that's but then in here that you need an array of m element. Okay, but the m could be very large. Yeah, let's take another example is a tire accumulation. Okay, so actually you don't need you don't need to keep m the a array with m size. Yeah, if especially if m is very large, then it takes up a lot of memory. Yeah, and as I said, that as long as the iteration, the loop t greater than the latency, then there will be enough. So you can choose appropriate small size tile. So that's a tile-based accumulation interleave. Okay, so the code will be looks like this one. So instead of you do the m operation, yeah, you save instead of using m element of a array, so you just do the tile, okay, given tile size t. Yeah, you just have need to have the t the accumulation buffer only need a tile of size t. Yeah, so you can greatly reduce as long as the t greater than the latency for this one. Okay, that'll be okay. Yeah, but once you do that, then this a need to read more times. Okay, before you just read once, that a value can fit into the m loop of calculation. But right now, since you tile, then the a array the A matrix, then you need to read multiple times. Yeah. So you basically trade off the storage with the memory access. Okay. So that's for the 1D, you do the tile to save the accumulation buffers. Yeah, but you have to pay the penalty to read the A matrix more times. Yeah. Okay, so another let's look at the investigate the OI, the operation intensity. Yeah. So for the matrix multiplication, that let's say the n is very large, that you could not save in the on chip. Okay, so everything is accessed from memory. Let's calculate the OI. We know the operation count is the n to the power 3. Okay, and then you have a multiplication and add. So that's the operation you perform for the whole matrix multiplication. Okay, for the memory access, that you need to read the A array and B array from the DRAM, and then you also write to the and in here that's to the power 3, because here that's n to the power 3. So you need to access A array and B array n to the power 3, and then you only need to write to C array n square. Okay, so you do the calculation, then you get the operation intensity like only 1/4. Okay, so let's say right now people use the black matrix techniques. Yeah, and so you do the you have a more for loop here, but the total iteration count is the same. Yeah, then you do the each sub block here. Okay, So the OI, we can calculate the OI for this loop. Okay, the OI here is the same as this part because only this part has the calculation. Yeah. So let's say that make the assumption the array of MB can fit into the on chip. Okay, you choose the right block size so that they can fit into the memory. Yeah, and the operation count is the same as this one, but right now the dimension become MB, the block size. Yeah, and for the external memory access, since the this MB this block can fit into the on-chip memory. So for the on-chip memory access A array and B array, since it is already saved in on-chip, so it's fast, so you can ignore it. So you only care about first time that you read from the off-chip. Okay, so that's you need to consider. Yeah, that's from the off-chip. Yeah, and that's the off-chip memory you write back to C. Yeah. So in this case, that's the OI you calculate. So you got this number. Yeah. So as long as the MB size equal greater than 2, then you get improved OI. Yeah. As long as the block size greater than 2, yeah, they will be better than this one. Yeah. So people try to localize the data access. Yeah, applying the block matrix multiplication. Yeah. Okay, so this is the code for the block matrix multiplication. Yeah, and in here, you basically let's in this example, this block matrix is 2 by 2. Okay, the block is 2 by 2. So there are 2 rows of A matrix and 2 columns of a B matrix will be used to calculate that. Yeah. So in this case, so for this part, the real kernel function is the block matrix matrix multiplication. Okay. So this part of the code you can think of it as a host code. This is a host code, and they only put the block matrix multiplication as the kernel function. Okay, so if you look at this kernel function, and so you basically read the row and then save this A array on chip. Okay, and then in this loop that they do the loop transformation, they put the K outside, okay, that's a external loop, and inner loop is the block size. Yeah, that's a yeah. So what it does is that's the access sequence for the A matrix, and this is the access sequence for the B matrix. Yeah. Okay. Yeah. So in here, this is a host program. If you want to make the full matrix as a kernel function, so you have to turn this host code, this part of a code, as the kernel function. Okay. In this case, this part will become the IOP. That's the IO processing. Yeah, for the memory IO access. So you can do the optimization to do the proper scheduling of data, and then save it in the local buffers, and then streaming into your block level multiplication kernel function here. You can think that that's the PE, and this become the IOP. Yeah. But the problem with this algorithm is you still need to cache the full row of A array. Yeah, and it's not scalable. because as I said, that if you have a AK by AK, yeah, so for two row of a matrix, it's still too big to fit into the chip memory. Yeah, yeah. For example, yeah. So this algorithm doesn't really scalable. Yeah, it's not scalable. Yeah. Okay, so next, let's talk about the tile scheme. That's a vertical folding, yeah, technique. So basically, it's similar to the block matrix multiplication. Yeah. Then it actually using the P processing element and doing the T tiles. Okay. So for this, then you need to keep accumulation buffer with the dimension T by P. Okay, and then you need to have since there's a P processing element, for each processing element you have a, A buffers. Okay, A buffers, so basically you try to cache in here, you try to cache the P row, only one element, okay, uh, from each K dimension, yeah. Okay, you try to cache these A buffers, and the A buffer will be repeatedly used. Okay, this is A buffer with a P element. Actually, P means the PPE. Okay, you times the A B matrix. So you cache this A buffer. So A buffer only read once, and then you read the B matrix uh, in this tile, T tiles of the B matrix. Yeah. Okay. So in this scheme that you actually separate the A array reading. Yeah. And so this part, while you reading the A array, then you can fit into the computation for this loop. Yeah, so you can do this part, these two part in parallel. Yeah. Okay. Yeah. So this is actually an basis for the next one, the next game. Yeah. Actually, this I put this as a special project topics. Uh, the reason is the matrix multiplication is very important, and also this paper and with the open source, they really provide a very good scalable architecture. Okay, the architecture is done in a way that first it's scalable that you can they actually parameterize, and those parameters depends on the size of PGA. Okay, so you can adjust that, and then the synthesized code will automatically generate the design for you. Okay, and they separate the I/O optimization from the computation. Yeah, that's I just introduced. That's the a good architectural method. Yeah, to do this way. Yeah, and also uh, the processing element is using the data flow. Okay, so the data is piped through each PE. Okay, so that they use local interconnections. Yeah. So with this scheme, that there is no problem in using the FPGA interconnection resource. Yeah, and they have various techniques. Um, So I will encourage you to read this paper and study this GitHub code. And this design, you can realize this design, and that can be very useful in your research project. Yeah. Okay. For this, I won't dip into detail because it's very verbose and very extensive, yeah, in this architecture. Yeah, it was worthwhile to spend a few months to really pick up this design. Okay, let's talk about convolution. Yeah, the convolution actually you are all very familiar with. Yeah, and yeah, first we all know we use the line buffer for the 2D convolutions. Yeah. Okay, so in here I probably don't talk much about. Yeah. So for the 2D convolution, that there are few data structures. Okay. First, you have an image size h height and w width. Yeah, and you have a kernel size is n times n. Yeah, and in doing the 2D convolution, it introduces several data structures. One is the line buffer. Okay, so you need a line buffer with n minus one lines. Okay, and you need to do you have a processing window, which is the kernel functions. Yeah, n by n. Yeah, and that's the kernel function. So the operation is you have a, in this case, there's a 3 by 3 kernel function, and thus you need two lines. Okay, there's a two line here, and the two line is actually the data is shifting into the line buffers. Okay, in this example, if you want to do the kernel function on this image, so you actually have a two line that you say that's the two line buffers. Okay, so you read in one new element, that this new element will shift into the line buffer. These called processing windows. This processing window, and the other two elements actually get from the line buffers. Okay, and then this new element will also push it into the line buffer and discard the previous element. Yeah. Okay. So in here, you will see the operation that you need to shift in two elements from the two line buffers. So these two line buffer need to be able to concurrent access for these two lines. Yeah. So that's why the line buffer, you need to have a user array partition and a partition with a dimension 1. Yeah. So that's a two line buffer. Two line has to be accessed concurrently. And also the processing window will do the convolution on the image concurrently. So this 3 by 3 processing window will be you need a partition complete. Yeah, because they will do the concurrent operation. Yeah, and also this processing window for each row, they actually doing the shifting functions. Yeah. Okay. So that's the operation for the 2D convolution. Yeah, I think this process you already familiar with. Okay, in here, what I like to talk about is convert the 2D convolution into 1D convolution. Yeah, and let's look at the complexity. Okay, so if the kernel function can be separable, that means this kernel function can be decomposed into vertical vector times a horizontal vector. For example, with this median filter, okay, that can be composed with this vertical vector and this horizontal vector. And in this example, there's a Gaussian filters that can be decomposed into this vertical vector and this horizontal vector. So when you time then you will get this kernel function. And that's a stable filter, horizontal stable filter, and there's a vertical stable filter. Yeah. So if the kernel function has these two attribute, one is separable, so that means that can be decomposed. And also it has associativity. That means the kernel function k is a vertical vector times the horizontal vector, and then convolute with the image. Then you can do the horizontal convolution first, and then do the vertical convolution in the second pass. Okay, if you can do that, then we can see you can gain the computation reduction. Yeah. So original convolution that you need that much computation. If you after you decompose, so you do the horizontal convolution first. That's the amount of computation you need. And then the second pass, so you actually add them together. So total computation actually reduce. Yeah, let's take kernel function 5 by 5. So the reduction becomes like 40% computation needed. Okay, yeah. So to do that, so we will do the horizontal convolution first, and then do the vertical convolution, and then we do handle the border case. And for each process, we like to do streaming. We like to do a streaming way. Yeah. To do that, it's not always get the equivalent result. The reason not always get the equivalent result is if that's a floating point operation, then that involve the rounding or truncation. Yeah. And the rounding and truncation really depend on the sequence of operation. Okay, so if it's the data is a floating point operation, then you may not get the equivalent result. Yeah, but it's a much simple and efficient. Yeah. However, look at this. You may not be faster than 2D convolution if you not implement correctly. Yeah. So that's a very important. So when you convert to the from 2D convolution, because 2D convolution we already know it can be done very efficient. Yeah, we all know the code. Yeah, but once you get convert to 1D convolution, then you will see it's not easy to write the code. The reason I particularly pick up these topics is I that really demonstrate how you can apply the data flow streaming architecture with this example. Because this example, from the first look, then you don't think that can be done efficiently. Yeah, we will see how the code is doing. Okay, let's see that's a very naive implementation. Okay, that's how you do the horizontal convolution. Let me briefly go through the diagram. Okay, so you do the horizontal configuration. Right now is a 5 by 5 kernel function. So horizontal filter is 5. Okay, so you shift in this way. Okay, so you get the result. Okay, and then you get the finally you get this intermediate result after the horizontal convolution. Then you use this horizontal convolution to work on the vertical convolution. So you have to have a local buffer to save the horizontal convolution result, and then you do the vertical convolution. Okay, so that's you do this way. Right now you do like this way. Okay, yeah, and then finally you get this vertical convolution. Yeah. And then you try to fix the boundary case, boundary. Yeah. So that's so this is the basic code structure. Yeah. This is basic code structure. Horizontal convolution, vertical convolution, and the boundary convolution. Yeah. Okay. And then for that you need a local buffer to. That's the local buffer you need. Yeah. How, okay, so let's look into the code. That's a very naive implementation. Let's look at what's the problem with this code. If we write this code, directly follow the diagram. So that's the way you write the code. So you go to the row by row, okay, and then you have each column, okay, and then and you do the calculation here. Okay, so that's a very naive implementation. Let's see what's the problem with this code. First, you need a local array. It's a local array. Okay, so for this local array, let's say that you are handling this size of image, then you need 8 MB memory. So local array save on chip is not feasible. Okay, with this code. Okay, so also when you write this code, that you first need to clear the local array. So it takes a lot of cycle to clear. Yeah. And the throughput is very limited because the source code has repeated. The source, remember this source is IO memory. Okay, that's the image saved in the DDR memory. So you have to repeatedly read. Okay, because the source is the top level function argument. So this is IOSS. Yeah. Okay, and also there's another problem here. Look at here. That's the loop H horizontal convolution, and actually this loop only loop 5 times. Only loop 5 times. Okay, so each time you have a loop entry and loop exit. It takes 1 cycle. Out of yeah, in 5 iteration, you have to spend 1 cycle in the loop and out exit the loop. Yeah. So this code is really not good. Yeah. And then let's look at the vertical convolution. Yeah. Great. So there's a vertical convolution doing this way, okay, vertically. Yeah. That's a sample code. So we do the vertical convolution. Yeah. So what's the issue? Again, that's the destination is the external image saved in the DDR memory. You have to clear the memory. Yeah, this is very stupid, right? Yeah, and then you have to read multiple read from the local pixel. Yeah, for the convolution, you have to do the multiple read. Yeah, and you also have to have a multiple write to the external port. Okay, and also the pixel, those pixels are processed down the row. Yeah, going this way. Yeah, so the access scheme is different from this array is produced, so it cannot be used for data flow or streaming. Remember, when you push in the array, you are doing this way, right? And when you read out the data, you're going this way. Yeah. So you cannot use the data flow. Okay. And so if you have a multiple frame to access this, this local buffer need to use a ping pong buffer, and you cannot use the stream. You cannot use a FIFO. You cannot use FIFO because the access sequence is different. Yeah. So if this kind of function is going to handle multiple frames, then you need to have a multiple local buffer. Yeah, using for the ping pong buffer. Yeah. So we already know the size cannot fit into the chip. Yeah. Okay. And here, let's say we handle the border. under the border. So that's how the code is written. Yeah, you can see you have a different loop. Yeah, that they are sequence of loop. Yeah. Then since the index they are all different, so you cannot do the loop merge. You cannot do the loop merge. So if I sequence the loop, then the latency you simply accumulate the loop latency, yeah, for each one. Yeah. And also you could not pipeline the top loop, yeah, because the sub loop has a variable bound. Yeah, so you cannot pipeline the top level loop. Yeah, and also the data access is in random access manner. Yeah. So for this naive implementation is really bad. Yeah. Yeah. You can write the code and let's see how many cycle it takes to compute. Yeah. So ideally, okay, we really like to have a design that we don't want to have a local buffer for image. And also, the source image only read once. Destination image only write once. Yeah, that's the basically that's the minimum. Yeah, and we want to be able to do the streaming data path. Yeah, so that we can pipeline in the frame. If there's a multiple frame fit into the convolution, we want to be able to pipeline the frame. Yeah, and we want to achieve minimum latency and the high throughput. That's the idea. Okay, let's see if we can really turn the uh, transform the naive implementation to meet the this requirement. Okay, so we will see how we transform the code. Okay, uh, here, you see my screen? Oh, okay, here. Okay, that's the scheme. Okay, first, we really like to have the image reading by so-called raster scan order. The raster scan order is how the image display on the screen. Yeah, that's the way you do the scan line and then retrace back to the next scan line. Okay, so that's so-called raster scan order, and this is also the order that scan on your screen. Okay, so we want the source image read read by the raster scan order. We also want the output destination image write out in this order, exactly this order. Yeah, and also read once and write once. Yeah. So that's the code structure. Let's look at the code structure. So that's the top function. So you have a source and destination all by streaming. Yeah. Why you want to have a streaming? Remember, this convolution may have they may not directly talk from system memory. They may be from another kernel function. Okay, remember we want the FPGA all implemented by the data flow. So we really like to have the I/O interface to be a streaming. So right now you have a streaming. Okay, so you're streaming the source, streaming in the source. Okay, and then you have uh, 3 block. Okay, once you're streaming in, then you want to do the horizontal convolution here. Okay, and then you want to streaming out to do the vertical convolution. And then you stream out to handle the border. And then you stream out to stream. Okay, so that's the block diagram for this code. Okay, and in here, we introduce two stream. Okay, so you declare two stream. That's a horizontal convolution string here. You declare a string here. You also declare a vertical convolution string, econ here. Okay, so right now you have a source string, intermediate you have a horizontal string, a v-convert string, and the destination string. Okay, and you look at this code. So you read from the source string and you write out to the horizontal convolution string. And next, that you have you also read it in, okay, and then you write it out, okay, and then you read it in, and then you write it out, okay, yeah, and you apply the data flow model, yeah, and within these two, remember for the vertical convolution, since it's doing the vertical, then you need to have a line buffer in between, yeah. So for the data flow architecture, if there are repeated access pattern, or it cannot be fit into a sequential access, in that case, then some kind of a local buffer will be introduced. Yeah, and line buffer is used for this purpose. So between the horizontal and vertical, you need to have a line buffer between. Okay, so that's the code, the whole code structure like this. Yeah. So that's the brief. You have an in-out transfer from the raster scan order. Yeah. The FPGA can transfer in the streaming manner. Yeah, and you ensure that a continuous flow of data reuse. Yeah. And you right now we don't need to have a local array. Yeah. And yeah, we use the string FIFO. That's the must reduce the storage and reduce the latency. Yeah. Okay. Okay, so that's the basic structure. Then let's look at the detail. There are very subtle detail in the coding to ensure uh, the data flow is really feasible. Okay, I will go through the code in detail. Okay, so right now let's do the horizontal convolution. And then you to do the convolution, you need to have a horizontal window. Okay, yeah. So so that's another cache buffer. That's used for cache the repeated data use. Yeah. And then in here, actually the horizontal window is performed in a shifter manner. So that's the loop doing the convolution and also doing the shifting here. Okay, and look at the code here. You put a pipeline outside this loop, right? Outside this horizontal convolution loop. So that means this part will be enrolled. Okay, so the 5 element of a horizontal convolution actually is done in parallel. Okay, so after this is done, then it will output. Okay, but look at the code here. Okay, so in here, this loop, you have a full row and column index. Remember, for the loop data flow canonical form, in that lecture, that you really want to have a increment, yeah, and you need to have a consistent the loop index, yeah. However, like not like the previous code, the index actually is changed, yeah. Then, but you only output, you write to the horizontal convolution output the stream under the condition. Yeah. Okay. So in here, that's remember the conditional operation is used in the loop. It's okay. Yeah. Remember, for the data flow, you don't want to have a condition outside the loop. Yeah, outside the loop, then evaluate the data flow mechanism. Yeah. So but it's good that you put the if conditional condition inside the loop. Okay. So conditional operation using there's no overhead as opposed to the CPU architecture, because CPU architecture really like to do this way. CPU doesn't architecture doesn't like have a if condition inside the loop. Yeah. For the FPGA, the HLS, actually we prefer this kind of coding. So we put this condition, yeah, inside this loop. So you will select the element to output. So you only output this part of element, yeah, into the string FIFO. Okay, so that's some key things in the coding. Yeah. Okay, right now let's look at the vertical convolution. Okay, and so remember the after the horizontal convolution, the data was get into the horizontal stream H convert string in this sequence. Okay, so when you try to read the data from the string FIFO, you have to follow exactly the same order. Okay. However, look at here. You only but for the vertical convolution, you actually access data in this way. Okay, you actually access data in this way. Yeah. Okay. Yeah. So then in this case, you need to have a line buffer. Okay. And right now it's a 5 by 5, so you need 4 lines. Yeah, there's a 4 line here. So you simply shift uh for each line you write it. Yeah. So for the shift, look at here. You have a 4 line. Okay, and this line here, each element you actually you need to shift in the data. Yeah. So let's look at the code. In here, look at here. You also have a two outside loop. You have the row loop and the column loop. Yeah. So exactly same as this order. Okay. Yeah. And then since the asset pattern is different, then you need to have a line buffer. That's where the line buffer introduced. Yeah. And for the line buffer, you shift the entry in this line buffer. Yeah. So when you fill the line buffer, okay, and then when the new entry after the fifth line, okay, when this element read in, you try to shift in, yeah, and then you do the convolution, yeah, here you get 5 elements, do the vertical convolution, yeah, and then you come down here, okay, yeah, and then you do the shift out, yeah, so you calculate another convolution here, yeah, get to the yeah this order. Okay, so you can study the code really carefully. So the key thing is you need k max 1 line for the line buffer. Okay, and In here, what you pay special attention is for the you want to make sure the H convolution stream is the same sequence as H convolution right. Yeah. And for the convolution right, look at here that you have this condition. And for the vertical convolution, you read with this. Look at the index. Look at the index. This index looks like it's different because the column greater than border width and column less than this. And this has to be exactly matched. The condition has to be exactly matched to ensure they are in line with the sequential access. Yeah. Okay, you can really study the code and find out that for the push and pop are exactly in the same sequence. Yeah. So that's the line buffer introduced. And right now you handle the border case. Yeah. For the border case, I probably don't get too much detail in here. Okay. Yeah. So again, here I emphasize that it actually you also have the same loop. Okay. If you look at that, you have a row loop. Okay, and you have a column loop. Yeah. That's exactly the same raster scan order. Yeah, that's how you output the destination image exactly with the raster scan order. And inside the code, you extensively use a conditional operation to sometimes you need to save the result in order for future processing. So they keep a few temporary buffers here. Okay, to do the boundary case. Yeah, the final destination image output, yeah, is in exactly raster scan order. Yeah. Okay. So if you reflect in the previous slide, yeah, it achieved this goal. Yeah, no local buffer for image, and source image only read once, destination only write once, and it's using the stream pipeline. Yeah, minimum latency. Yeah. And during the process, you use a very small localized cache, like the window buffers and the line buffers, hold the result. And important is, yeah, it perform the conditional branch inside the pipeline test. Yeah, they use all kind of a conditional statement to keep the data access in sequence. Yeah, if they are not in sequence, then they use the local buffer to save it. Yeah. Okay. So I really like you to get the insight or really understand this 1D convolution example. Yeah, and that example is serve the techniques used in this example can be applied to many of the image processing, a similar type of computation. Okay, yeah. The last let's talk about systolic array. Yeah, I will use the Smith-Waterman algorithm. Yeah, Smith-Waterman algorithm is a algorithm used for the DNA sequence searching. Yeah. Okay. So first, why we really like the systolic array architectures? Yeah, that's a typical diagram, but this diagram is not related to the slide in the later use. Simply show how they are connected. Yeah. So for systolic array, there are a few characteristics. Okay, first, they are homogeneous parallel pipeline computing. That means each processing element are exactly the same. Yeah, they are homogeneous. Yeah, and they are evaluated synchronously. So every cycle, every processing element operate at the same time. Yeah, and another key feature is they have a spatial and temporal locality. That's important. So that's why all the data information passing all use a local interconnection. Yeah, they only transfer the data to its neighboring processing element. And this architecture is very scalable. Yeah. Okay. So the advantage to use the systolic array architecture is it's a highly parallelism. Yeah. You can see each processing element they are running at the same time, and the utilization is 100%. Okay, it's not like many of the parallel architecture that sometimes you have to wait for the data. Yeah, so that processing element actually is idle. Yeah, so when you calculate the computation power, don't just look at how many processing element times frequency. A lot of people simply calculate the processing power. It's that simple. It's wrong because the processing element may not be 100% utilized. May not be 100% utilized. Most of the time, they are waiting for data. Yeah. For serial array, they get the data from the neighbor. Yeah. So every element operate synchronously. So every cycle, they do the evaluation and produce the output. So make the next processing element SQ. Yeah. The data is there. Right. So serial array can have a very, very high computation utilization. Yeah, that's very key. Yeah, and it's using the data flow. Yeah, and it's good for FPGA architecture because it has only a local connectivity. Yeah, so so when you encounter a problem, yeah, first think whether that problem can be transformed into the systolic array. Yeah, that's a very efficient architecture. Yeah. Okay, so let's brief about the this Smith-Waterman algorithm. Okay, so basically, you have a query gene sequence, and then you have a database. Okay, and then you try to matching, find the alignment between these two nucleotide or the protein sequence. So this is a type of dynamic programming, yeah, and it's a very highly compute intensive. It has many applications besides the computational biology. Yeah, the application in the area of like a similar document retrieval or near duplicate web page detection or finger point or deep packet socket, deep packet inspection. Deep packet inspection is that's the network packet comes in, then they uh, investigate the content of the packet. So that's the the virus detection. Yeah, you want to find out the packet, the network packet, if there is a certain attribute or certain pattern in the content of the packet. Yeah, so it's a very useful in the deep packet inspection. So they all use the similar computation. Yeah. So let's let me quickly explain how this algorithm uh, works. So you have a query string, okay, and then you have a database with size m. Normally m is much larger than n. Okay, a big long string of characters, and you want to find out whether the query pattern maximally match in part of the database. Yeah. So to do that, you have to construct a similarity matrix. Okay, the similarity matrix. This is a similarity matrix. So you will have the first row and first column initialized to 0. Okay, and then this is the query string, and this is in the y direction is a database character string. Yeah, and for the content of the each element of the similarity matrix is calculated based on this formula. Okay, so let's take this example. Okay, let's say for this element of the similarity matrix, it will based on the northwest corner and then compute these two character. If these two character is match, okay, you add certain point. In this example, you add 5 points. If this mismatch, then you minus 3. Okay. Okay, so that's this one. Okay. Or if coming down this direction, yeah, the same minus 1, that means the row, previous row. So that's the north direction. If the north element, you minus the delete cost. Okay. And for the right, okay, they're coming from the left side. Okay. You have the insert cost. Yeah. So in this case, this is different. So you minus 3, so you got 2, and this 1 minus 4 becomes minus 3, and this coming the west direction is minus 4, and this. So you choose the maximum value. So this is 2. Okay. So that's how you construct the similarity matrix. You're going from this direction, yeah, and then you propagate down. Okay, and then you want to find the sequence, so you also need to keep track the traceback matrix. For example, this element, this value is got from the northwest, yeah, so that's why in the traceback matrix you mark down there's a northwest, so that you can trace back. So that's the example here that we can find out after you evaluate this database, you keep track the maximum value. Okay, currently there are 2 maximum value. Yeah, so then you trace back. You use the traceback matrix. You go find out. Okay, that's the matching. Uh, give you the maximum value of alignment. Yeah, so you got this. Okay. Yeah. So that's the result. Yeah. So whenever you go in this direction, so it is the delete. Okay. Yeah. For example, like here, that's a query string. That's a database. Yeah. And then that's a you insert in the query. That's a you delete. Yeah. Depending on whether you going this direction or you coming this path. Yeah. Okay, so that's the Smith-Waterman algorithm. Yeah. Okay. For this algorithm, it's a naturally uh, fit into the systolic array. We find out you do the calculation from the upper left corner. You starting from this, okay, and then you start calculate. You calculate this and you calculate this, and then you coming down. You calculate this. Yeah. Okay. So it's and then we find out the anti-diagonal element, anti-diagonal diagonal element, they are independent operation. There is no data dependency on this direction. Okay, and when you calculate a value, for example, for this value you calculate, you depend on the north element and the left on the west element, and these two elements is in the previous scan line, and the northwest is the previous two anti-diagonal value. Okay, so to calculate value, you need to use the two previous anti-diagonal value. That's it's a characteristic. Yeah, and so to calculate that, you can use NPE. N is the dimension of the carrier string. Yeah, so actually in this example, you have a the query size is 3, so you need a 3 PE. Yeah, and then you need to compute a total take m plus n minus 1 cycle. Yeah. Okay, so that's how you calculate like this one. Yeah. So the total number of cycle it takes is m plus n minus 1 cycle. Yeah, and each PE computes some function, and each PE receives data either from the query string or from the database, or from the previous iteration, the northwest, the 3 value from previous or the one before previous. Yeah. So that's how it operates. Yeah. Okay. So that's the systolic array of the P operation. So right now, you pretty much know how this algorithm is operated. Yeah. So for each PE, for example, for this PE, the result, okay, the output will be used for the west of the successive that's the next PE. Okay, so for this result for the next cycle, the next scan line, that it will be used for the west value of the next PE, or the north value of the same PE. Okay, or its north value, its this element, the north value will become the next scan line, the northwest. Okay, so that's where the output goes. Okay, so that's the operation. Let's look at the code. Okay, and the code, this is not a full code, but the code size is not big, like only 100, less than 200 line of code. So the code size is small. But what's important is how do you write the C code that will have the structure, systolic array structures. Yeah. And in this example, this systolic array is only 1D systolic array. Okay, you may construct a 2D systolic array, and they will be most likely the same. You just use the 2-for loop. Okay, but in this example, it's only because there's a scan line. Yeah, that's 1D systolic array. Yeah. Okay. So in this example, we need to pay attention to some of the data structure you use. Okay. First, you do need to have two array. One is for the query string. The string one is the query string. String is the database string. Okay, and this two array has to be fully complete partition. Yeah, because the PE operate concurrently, so you need to feed the data, yeah, for the query and for the database. Yeah. So you need to be able to read every element of the query and the database. The database is not the full database. That's one area that can be optimized. Yeah, for the database is very big. Yeah, then it's not necessary to all save in the memory. Yeah, that's another optimization you can do. Yeah, and also remember we need to have a north array, we need to have a west, and we need to have a northwest array. Okay, and this array actually you need fully partition because PE will ask them all the time. Yeah, so that's why you need a partition always. Okay, and you need to have around that many cycles. So you have a for loop with n plus m minus 1 iteration. Okay, and then you will call calculate diagonal. Yeah, and in the calculate diagonal is the PE operation. Yeah, that's the scan line for each PE. So the calculate diagonal. So you will have a for loop. This for loop represent number of PE. And right now, the number of PE equal the query n, Yeah, okay. And the inside, you simply write down the equation. Yeah. Okay, there are 2 points I want to point out here. Okay. First, remember, look at here that for the output, let's go back. Okay. Look at how the output will to the next iteration, it will go to the west of a successive PE. Okay, so that means the output, the calculation output will go to next PE. So when you write the C code, you have to look at here, the index is going from upper MS1 to 0. So you actually evaluate the PE in this direction, right? From n-1 to 0. Okay, so that's why when you assign this equation, yeah, when you assign the index plus 1, that will be used in the next iteration. Yeah, if you write the for loop from 0 to n-1, you will find out the value just falls to the next p. Yeah. So that's important here. Yeah, to make sure. Yeah, you have to write the loop index in this order. Otherwise, the result will not be correct. Yeah, that's one thing. Another thing, in this code, another thing you need to pay attention is it uses inline. Okay, the code is written in this way is for clarity, so for people to easily understand the code. Okay, but to make the HLS to synthesize a correct hardware, that you have to inline this code. Look at here, you do the inline. Okay, so inline means this for loop. This for loop is promote to this level. Okay, this function boundaries disappear. Okay, so this for loop is actually, if you rewrite the code, then this for loop will be in here, directly under this for loop. Okay, and then you put the pipeline here. Okay, so this pipeline is outside this for loop. That means this for loop will be enrolled. Okay, so you will have a NPE. So that's the operational over a PE. Okay, and you enroll. So you will instantiate NPE. Okay, so that's the code structure to generate a 1D systolic array. Yeah. So for 2D systolic array, yeah, it's not much different. You simply use a two-level loop. Yeah, and then you put the P operation inside the inner loop, and then you enroll them. Yeah, you try to enroll this two for loop, or you put a pipeline here. Yeah, you put a pipeline here, then this two-level for loop will be enrolled. Yeah. Okay, so that's the basic coding structure that to instantiate an systolic array. Yeah. Okay, there are other improvement. Yeah. So I just that's not the key message. The key message is how to write the C code to generate the systolic array. Yeah. Okay. So pretty much cover the topics today. Yeah. Okay. So is there any question? Okay. Can you tell me what percentage of your understanding for today's topics? Let's go back to the very beginning. Yeah. Yeah. Here. Okay, we talk about the architectural framework, the memory access scheme, and this I think a very one is a very classic and very useful architecture that can be used in your acceleration problem. Okay. Wow. Darren, you have understand only 30%. Tell me which part is most difficult for you. These topics, which one is most unclear to you?
Actually, the last part.
Systolic array.
Yes.
Oh.
Actually,
And
for the first
mm.
three part, I understand the concept, but the detail I have to track the code after class.
Right. Yeah.
Yeah, but
Do need to
for
go to yeah.
systolic array, I really just understand the concept.
Totally. Oh. Okay. First, let me ask you: do you understand this algorithm operation?
Mm, not really.
Not quite. Oh,
Yeah.
you don't know how this is calculated. Yeah.
Yes. But I
Okay. But
understand the
yeah. Mm.
why we have to use the syntolic array.
Uh-huh.
But the detail how to do it, I have to study more.
Yeah. Okay. So basically here, you know the calculation sequence, the calculation formula. That's how they calculate. Okay. And then calculate is going on this direction. You know, that's how you calculate.
Uh huh. Yes.
Yeah, like wave front, you propagate in this way.
Yes.
Okay, that's one key thing. And the second key thing is for this anti-diagonal, they can actually run in parallel. There's no data dependency among the element on this anti-diagonal. Okay, you just assume it. Okay, believe it.
Mm-hmm.
Okay, for now. Okay, and then it talk about what the data coming from for each element. For example, this element, to do the calculation, you need get data from these three. Okay, from north, from west, from northwest.
Mm-hmm.
Okay, so that, and then this north, west, and northwest, you have to save them. So you have a 3 array for these 3. Okay, and each PE, when you calculate, then you will update this north, west, and northwest array content. And that will be used for the next iteration use.
Oh.
Okay.
Mm-hmm.
So basically, you get the idea. So what's important here? If you know roughly the operations step, and in this slide, I simply want to say how to write the code to do that kind of operation. Okay, so you definitely know you will have a 2 array for the input string, yeah, the query string and that one, and then you need to have a 3 array to keep track the northwest and northwest value.
Mm-hmm.
Okay, and then you come to, for each PE operation, that's the PE operation. Okay, so here basically that's the equation we introduced. For northwest, you add the scope function match. For north coming down, you have the delete insert value. So you calculate 3 value, and the 3 value you calculate the maximum value. You choose the maximum value based on that equation. Remember this equation? Yeah, here. Okay, so this part of a code simply reflects this equation. Okay, and then you calculate. So that's the PE output value. The PE output value will need to update the northwest, north and west for to be used for next iteration. Okay, so that's, yeah. So right now for writing this code, there are two key things very important. Okay, one is I emphasize this array index because that's kind of a structured design that if like a shift, remember like a shift register, right? Shift register, you shift from the higher order to lower order, right? When you write the
Yeah.
code for shifter,
Uh-huh.
yeah, you don't write in this order. Yeah, you write in this order. Okay, just like a pipeline. If remember the structural design, if it's a pipeline stage, when you write the code, you write in this order, right?
Yes.
Yeah. Otherwise, the C code won't match with the hardware. Yeah, the same idea. Then you have to write. This is like a shifting idea. So you have the for loop from the higher index to lower index. It's like a shifting.
Okay.
Yeah, so that's one thing I point out. You have to write this way, otherwise not correct. And the second thing is you really want to have a multiple PE instantiate, right? Yeah. So you need to do the enroll. Yeah. So to understand this code, this is kind of tricky. Then you have to understand that first you have to the inline. When you inline, you pull the for loop upper. Yeah, you remove this function boundary, and then you find out the pipeline is outside this for loop, right? Yeah, remember if a pipeline outside the for loop, then this for loop will be enrolled, right? Yeah, so that means that all the logic here will be duplicate for n times. Yeah, so that's how you form the NPE. Yeah, n duplicate of a PE function.
Okay.
Yeah. And yeah, so you can always reference this code to write your systolic array. And this is 1D. For 2D, as I say, just a 2 level of for loop. Then you can do that.
Okay.
Okay. Right now, you got 80%?
Maybe 16. 50 or 60.
50, 60. Okay. Yeah. I put the code here. Yeah, you do need to go back to really study. For this PPT, actually I rewrite some of the code because from the document I don't think that their code is correct. Yeah, because it's document. Nobody really wrong the code written in the document. So the code in the document I don't think is right. So I rewrite some of the code. Yeah, at least makes sense to me. Yeah. So, but I do study those code a lot. Yeah, try to really understand. So you should do the same. Yeah, really study those code. Yeah, and make sure you fully understand and make the code as yours. Yeah.
Okay, thanks.
Okay. Good. Yeah. Okay. Hopefully you all can master the HUS. But however, uh, you do need to write the code from scratch. Not necessarily from scratch. At least if you have a algorithm with the source code, and not for the HUS, but you do a series of optimization efforts and implement that in a high efficient, high performance HUS coding. Yeah, you have to go through this process. Yeah. Mm. Hopefully, yeah, you can learn a lot from this lecture. Yeah. Okay. Yeah. So next week, yeah, I'm looking forward to your final project. Yeah. As I said, if you're running into difficulties, yeah, don't hesitate, talk to me. Yeah, we can discuss how to adapt or readjust your scope. Yeah, and you have a difficulty complete the final project, and we can delay the submission of the final grade that give you more time to work on it. Yeah. Okay. Yeah. So we will conclude today's lecture. Yeah. Okay. Yeah. So thanks. Yeah. Let's see next week.